2 times 3 is 6, so 45, which definitely does not equal 0, therefore these two vectors are not perpendicular. Well, what else can we use this idea of a dot product for? And this is pretty clever. Turns out that if these two vectors are unit vectors, then the dot product represents the cosine of the angle between them. So what we can do is we can go through and say that if u and v are unit vectors, in this case they're obviously not, but that's okay, then cosine of alpha is equal to u dot v. Well, what do we do in the case where we're not dealing with unit vectors? And by the way, why might we be interested in figuring out the angle between two vectors? Let's say that we just place a motion on one of our axes here. We move this axis, say, 2 steps from here to here, or whatever, 2 encoder steps on the motor. Well, do we necessarily, we should know, but do we necessarily know for certain what the angular displacement is? No, but if we're keeping track of the new position of that input vector, then we could go through and determine the angular displacement between those 2 points. Okay. So kind of useful there. Within the robotic system, we'll be going through and using these dot products periodically to figure out the angle of separation between 2 vectors. Okay, so if u and v are not unit vectors, then all we have to do is convert them to unit vectors. Okay, so in the general case, we can say that cosine of the angle between the vectors is equal to u over the magnitude of u time, or dot v over the magnitude of v. What did I do? This is, of course, the problem with having a lecture class in here, because we have to look around everything. But what we're going to see is after we get through the first probably 2 weeks of lecture, and this week and next week, then we're going to switch much more to a lab-based class. So that's the reason why we're actually in here. So all we did here was we said, okay, well, if u is not a unit vector, well, even if it is a unit vector, we're just going to take that vector divided by its magnitude to make sure it's expressed as a unit vector. Good? So, in this case, if we wanted to go through and solve for our angle alpha, we could just hit both sides with arc cosine. So we could say that our angle alpha is equal to the inverse cosine of, let's see, u over the magnitude of u times v over the magnitude of v. Okay. For those of you that have seen this in other places, you may have seen it as, let's see, what would it be? Maybe u dot v is equal to magnitude of u times magnitude of v times the cosine of the angle between the vectors. And that's simply the same expression, it's just rearranged differently to express it in much more of a equation format rather than the format that I expressed here. Is that how you saw it in statics? Or have you had statics yet? No. I think this is the way that it's expressed in statics when you get there. So.
What physics 183 and calc 3 did also.
Really? Okay. So. Okay. So let's go ahead and do an example. Let's go ahead and find that angle between these two vectors, u and v then. What's the first thing we're gonna do? I'll go ahead and clear the board and throw these up here on towards the top. So we have u equal to 5, 2, 2. We've already, I believe, converted that to the unit vector. V is equal to 7, 2, 3. So if we want to express u, oh, this will be clever. U as a unit vector, it'll be u sub u, which will equal, let's see, 5 divided by the magnitude of the vector, it was 33. Square root of 33. And 2 over square root of 33, and 2 over square root of 33, which we could express as 1 over square root of 33 times 5, 2, 2. Everyone okay with making that step? Okay, all this is doing is expressing it as u divided by the magnitude of u. That's the reason I did that. And then v expressed as a unit vector within b, let's see, we've got 49 plus 4, that's 53, plus another 9, 62. So we'd have 1 over square root of 62 times 7, 2, 3. So with that being said then, we can, now that we have these expressed as unit vectors, we can say that cosine of alpha is equal to u dot v over magnitude of u times magnitude of v, which would give us, let's see, 5, 2, 2 dot 7, 2, 3, all over the square root of 33 times the square root of 62. And let's see, that would be 35 plus 4 plus, yeah, I already did that, so 45 divided by the square root of 33 times the square root of 62. And what's that give us there? Boy, I thought these hour-and-a-half classes were going to be difficult, but they're actually going to fly by, aren't they?
45.23.
45.23. Oh, degrees.
Times the square root of 33 times the square root of 62.
Okay, did you take the
I didn't do,
45 divided by that 45 point?
which is 0.99 degrees.
But it,
0.99.
0.99 degrees. So in this case, these two vectors are almost pointing in the same direction. Oh, and that actually makes sense if we look at them. We'll draw them on the board here in a second. So we have 45 over 45 and some change. What did you say, 45.3?
0.23.
23. So this is going to equal 0.99-ish, and we know that alpha then is going to equal the inverse cosine of 0.99, which is going to be a really small angle, 1, maybe 2 degrees.
So 5.8 degrees.
What is it?
5.8.
Wow, really? That's a lot
So
of
it's
weight.
0.141, cosine inverse is 0.99, that we said?
Yeah,
Yeah.
You guys on degrees or radians?
yeah, no kidding. Because I only concern myself with degrees. I would have brought my calculator,
Yeah,
but
it's like 8.1.
8.1 degrees.
Yeah.
Okay, and of course, if you're using the more accurate approximation, then you probably have a slightly different answer here. Okay, so how can we kind of attempt to visualize this to see if this makes sense?
Draw the vectors in 3 dimensions.
Yeah, we can go through and draw the vectors in 3 dimensions, so I'll try to do that. So I'm going to do the same thing here. I'm going to go through and say that my z-axis is here. This is one of my 2 axes, this is the other 2 axes. Ideally, they intersect. So this is z plus. This is our x plus, and this is our y plus. And so we have our first vector. I'll do it, what do you want, blue? So we're going to come along the x-axis 5 units, 1, 2, 3, 4, 5. We're going to go in the positive y direction 2, 1, 2, and we're going to go in the positive z direction 3. So we're going to go up 1, 2. How did I get 3 out of that? Okay, so there's our, if I scribble on it enough, it'll look better. There's our vector u. That makes sense. This is a pretty common approach to drawing 3-dimensional vectors, is to do your x, then your y, then your z translations. That way you can map it out in 3 space. Okay. And then our v vector goes along the x-axis 7 over 2 and that direction, y, and then up 3. So 1, 2, 3. So right here is our v vector, and sure enough, we can see that the angle between those 2 vectors is pretty small. Keep in mind that this is just a very rough sketch. I mean, we probably would not try to take any kind of measurements, because in order to truly represent that angle, what we'd have to do is lay the resulting plane flat in order to take our protractor or whatever instrument we're using to measure the angle. That makes sense? So it's a good idea to start practicing drawing these 3-dimensional representations, because if we have, let's say, a robot configuration that has rotated about the z-axis a certain number of degrees, and then elevated a certain distance, we would want to be able to represent that robot in 3-dimensional space. And then from here, we might elevate it more on the second joint and so on and so forth. The ideal thing that you're going to see, or the thing that you're going to see us doing, is essentially casting the shadow or the projection on the XY plane and using that projection to relate each of the elements in 3 space. That makes sense? Okay, so we've got dot products out of the way. Any questions up until now? We're going to be using these over and over again as we go through the course. So even if you're not real comfortable with these vector operations now, we'll be using them so often that ultimately it'll become second nature to you. Early on, these are just academic in nature. They're just intended to build the framework for what we'll be doing later on. When we get into MATLAB in week 3 or 4, MATLAB is going to be doing all of this stuff for us. The thing that we need to do is keep in mind that, you know, when we set up the equations to do the work for us, that we can't, that we have to have a column vector and a row vector figured properly in order to perform the calculation the way we intend it. Okay? So with this then, we can go on into our matrix representations. Okay, and a matrix we can say is, yeah, for our purposes, a set of vectors used to define a plane or space. Ideally, we want to be able to define a space because that robot is moving through space. But in the case of a scalar robot, as we discussed yesterday, we may only need to model that robot on a single plane and then just translate that plane up and down in order to move those wafers around. Okay? If we want to do matrix multiplication, this is nothing more than applying the dot product, the scalar product or dot product to each row and column of the two matrices. Okay, as an example, in this case, let's say that we have a very unimaginative matrix. 2, 3, 4, 5, 6, and a slightly more interesting matrix. That's going to show up a lot, so. What's one thing we have to check when performing this matrix multiplication?
Inner dimensions have to match.
Inner dimensions have to match. So the number of columns of the first matrix have to match the number of rows of the second. And the reason for this is because we're going to take the dot product of the first row and the first column, then the dot product of the first row and any subsequent columns. Okay? So we have to make sure that columns of first matrix matches rows of second matrix. Okay? And in this case they do, therefore we can go through and take the dot product of the first row, first column, and then of the second row and first column. So this is going to be, let's see, 2 times 7, wait, 1 times 7 is 7, plus 2 times 2 is 4, plus 3 times 3 is 9. And then our second row by first column is 7 times 6 is 42, plus 5 times 2 is 10, plus 4 times 3 is 12. Therefore, the matrix multiplication results in a, let's see, that's 11, 20, and then 42, 52, 64. So we end up with a two-dimensional vector equal to 20, 64. What's interesting about the solution? Particularly about the dimensions of the solution. Okay, in order to see if we can perform the operation, we need to check the inside dimensions. The solution will take on the outside dimensions. In this case, we see that we have a 2-row by 1-column solution, okay? So, and number of rows first by number of columns of second. So that's a real good way to at least check to see if you're on the right track when you're performing this matrix multiplication. What if we had changed these two around? What if we had tried to go through and say we want to take 7, 2, 3 times 1, 2, 3, 4, 5, 6, 5, 4. In this case, we can't do it because we would need to have 2 columns or 1 row. Either 2 columns in the first matrix or 1 row in the second matrix in order to ensure compatibility between the 2 matrices. So this operation is not possible. And this is going to result in a bunch of problems in MATLAB if you're not paying attention. Because if you go through and perform your matrix operations, and we're going to be performing matrix operations like mad, okay? If you're trying to perform your matrix operations incorrectly, MATLAB will just throw up an error. It's not going to provide any real information to you. It's just going to say, can't do that, okay? So you really have to pay attention to your matrix operations when you're setting up your code. Good? Okay, so, oh, okay.
So what's the rule of thumb if it's the other way around? Is it then the number of rows of the first, the number of rows in the first matrix has to be the number of columns in the second? Or is it just?
No, you always, when you're checking your matrices, always make sure the columns of the first is equal to the rows of the
So
second.
it's just better to set it up that way than to set it up the bottom way, so it's always better to set up the way. Okay.
Right. When we go through and work with this stuff in MATLAB, what we'll always do is we'll have a rotation matrix here, which will have our R11, our row 1, 2, R13, R21, R22, R23, R31, R32, and R33. So this will just be a rotation matrix, and we'll learn more about rotation matrices here in a little bit. And then we'll have a position vector, P1, P2, well, I better say row 1, column 1. So when we go through and do this, what we'll see is that if we want to go through and rotate this position vector, we have to take the matrix times the vector and not the other way around. If we take the vector times the matrix, then the vector has to be arranged in a row vector in order to get the job done. So we have to have P 1, 1, P 1, 2, P 1, 3 times the rotation matrix. But we have to be careful because that's not necessarily going to result in the same thing. That makes sense. Okay. So this is the format that we're going to use when we're performing these transformations and translations in MATLAB. Okay, so one of the very nice things that we can do with matrices, and I could have saved myself a little bit of marker here, is we can define these orthonormal matrices. And most of the time, we want to define these orthonormal matrices because they are incredibly easy to work with, okay? For example, if we have a rotation matrix set up correctly, 1, 1, I should not have erased that. Okay, so row 1, column 2, row 1, column 3. Let's see, 3, 1, row 3, 2. Okay, if this rotation matrix is set up like this and it is orthonormal, then inverting this